All right, let's see the example together. If a total load of 12,000 kilonewton is on top on the 8 piles, and the piles are arranged in a 2 multiply 4 pattern, which means a rectangular pattern, right? With a spacing of 2.5 meter in both directions. The first of all, okay, the spacing means the center to center, C to C distance between the piles, Sorry. So the center to center this distance from the vertical direction and the horizontal direction actually are always equal to 2.5 meter, and determine the pile settlement under this case. Okay, this is the first part, first half, okay, of this question. And the second half is if an additional moment is applied, okay, in the long direction, and determine the various pile loads and settlement of each pile, assuming a rigid cap. Okay, so let's see the first section first. And as you see here, this question actually is a pile group question. Okay, as we discussed in the lecture, for pile group, the calculation is just we have some revision. Okay, on the equations of for the single pile on the vertical loading, right? And the first revision is the Rm. Rm is equal to this equation. Okay, equal to this equation. We have one more additional parameter, Rg here. Okay, Rg is the radius of the equivalent circle. Okay, the area of the equivalent circle is equal to the area of the circumferential area of these 8 piles. Okay, the area of these 8 piles is in this red dashed rectangle. Okay, rather than the rigid cap. Okay, rather than the blue dashed line rectangle. Okay, they are different. So the Rg is equal to, okay, for example, equivalent circle is like this. Okay, this circle has the same area as this red dashed rectangle. Okay, so Rg is the radius. This is equal to Rg. Okay, so rho 2.5 times rho, okay, this bracket and L. This is the Poisson ratio. L is the embedded length of the pile, and this rho is equal to GAV divided by GE, the average shear modulus of the soil along the depth divided by the shear modulus of the soil at the pile end, right? And the GAV here is equal to GE, okay, for this example, because the soil is assumed uniform, okay, along the pile depth. So this one is equal to 1. And Rm, okay, represented by this equation. And this is the first revision, okay, for the calculation of pile group. And the second one is about the so-called influence factor, okay, influence factor. So you see here, omega 0 is equal to P0 FII, right? This is for the calculation of the settlement of the pile under the force, P0, okay? The settlement of the 0, this one, for example, the pile I, okay? The pile I, the settlement of pile I is equal to the force on pile I multiply FII. Okay, FII represents the influence factor due to the pile force on the top of itself. Okay, and we are going to do the second revision about for the FII value. Okay, if we are going to calculate the settlement due to the influence of other piles, we will use Fij, right? The influence of pile J to the settlement of pile I. Okay, this is the definition of pile Fij. So Fij, the equation is listed here. The thing we are going to do is to replace K1 and 2 by K1 prime and K2 prime. Okay, you can see here K1 prime, K2 prime. Okay, K1 prime is K1 multiplied natural log Rm over R0, then over natural log Rm R. Okay, here we have a R value here. Similarly, for K2 prime, we have another R. Okay, so this R, okay, even though it is R, but actually it is a distance. Okay, center to center distance between pile I and pile J. Okay, center to center distance. For example, center here for pile 5, center here for pile 7. So the center to center spacing, for example, F5, 7. Okay, if we are going to calculate this one, the R here is equal to 2.5, right? 2.5 center to center distance. So this is a definition of R value, okay, of R value. The only new parameter here is R, okay, for the correction or for the revision for the Fij expression, okay. So we are going to be careful about the R value, okay, R value. So for calculating the FRG, okay, we first establish the equilibrium between the two areas. The first area is the equivalent circle, and this area is the area of rectangle, right? Rectangle. As I said, if we have a circumferential area for this pile group, the length for this rectangle is equal to 2.5 multiplied 3 here to here. Center to center distance between pile 1 and pile 7, right? But if we are going to calculate the circumferential rectangle's length, actually we have two more radius. One is here, one is here. Both of them is equal to 0.25. Okay, so that we have 0.5 here, which is equal to 0.25 multiplied 2. Okay, so this is a real length for this circumferential rectangle for this pile group. And similarly, we have the width of this rectangle, 2.5, the center to center distance, plus the 2 radius, okay, 0.5 here. Then we can get the Rg value as shown here, right? And Rm can be calculated using this equation we already discussed. And the value for Rm is 42.76 meter, okay, meter. Okay, meter. And the zeta is equal to natural log Rm over R0, which is equal to 5.142, okay? This is zeta. And this zeta value is used in the equation 19, right? If you still remember. And the K1 and K2 can be calculated here. And as I mentioned to you in the lecture, okay, this K2, this one, okay, this equation actually is get from the mechanics of plasticity, okay? So this is theoretical result equation, okay? Normally this one will be directly give to you, okay, because this is based on the mechanics of plasticity. So we have this equation here for K2, and K1 is equal to this equation. We have G, we have zeta, right? And we have K1, K2 value. And U is equal to this equation, okay? And you can see here, the APEP, okay? AP is the pile area, okay? You should be careful because this pile actually is a hollow pile, okay? A hollow center part. And EP is the Young's modulus of this pile. Okay, normally for the question in lecture 2, you should be careful about the Young's modulus and the shear modulus, okay? Normally we will use shear modulus for soil and Young's modulus for pile, okay? And if you are going to calculate the shear modulus of the soil from the Young's modulus of the soil. Okay, we are going to use this equation. We already discussed this one. Okay, you'd better to remember this equation. Okay, the relationship between shear modulus of soil and the Young's modulus of the soil based on the Poisson ratio. Okay, so we get this. This is u, this is mu. Okay, they are different, and this u is just a parameter here, and equal to this value. And okay, this one you can also calculate very easily. And the FII is the influence factor of the ice pile itself, right? And FII, we get this equation already. And this is the result. This is the value, okay? So this is for FII. Finish. For calculate the influence due to the pile on itself, the force on itself. Then we are going to calculate the influence of other piles on the settlement of this pile. Okay, for example, the pile 1, the settlement of pile 1 contributed by the pile 3. Okay, so first of all, as I mentioned to you, the only thing matter is the distance. Okay, this is not the radius, it's the distance between two piles. Okay, you can see here. For the pile 1, let's see the R value from pile 3 to pile 1 is equal to 2.5 meters, right? Center to center, which is equal to the distance between pile 2 and pile 1. It's also equal to 2.5 meters, right? Okay, so you can directly have this conclusion: F12 will be equal to F13, right? Because the R between these two pairs are the same. Okay, and for the pile 4, we have another distance here, right? And for pile 6 and pile 1, we have another distance. Pile 5, similarly, we have another distance. Pile 8, we have another one. Pile 7, we have the final one. Okay, pile 7. So you can see we have, okay, how many distance to calculate the settlement of pile 1. Okay, this is the first one. They are the same. They are the same. The first one. Okay. Second one, third one, fourth one, fifth one, and sixth one. Right. So for pile 1, we actually have 6 different R values, which means we have 6 different Fij. Okay, this I actually is 1, right? We have 6, and plus one more Fii represent the influence by itself. Okay, the force on top of itself. So we actually have 7 different values of influence factor. Okay, but for 2 and 3, actually we use the same value. Okay, you can imagine that, right? So let's make another example. Okay, for example, randomly pile 6. Okay, pile 6. F64. Okay, you can see will be equal to F65, right? Because the distance are the same. Will be equal to F68. Okay, all the distance here are equal to 2.5 meters, right? And we have this one, we have this one. So F63 will be equal to F67, right? Because the distance is the same, right? So how about F1? Okay, we have another distance. And here from pile 2, we have another distance. We have another distance, okay? How many distance here? 1, 2, 3, 4, right? So for calculating the settlement of pile 6, it has 4 different distance, so that it has 4 F6J, right? And plus FII, F66, right? So it has 4 F5 in total, different influence factor, right? It has 5, and for power 1, it has 7. Okay, it has 7. Here we have 5. So this is the different conditions for different powers when calculating, determining the influence factor. Okay, so let's see. For calculate the F13, okay, F13, the R is equal to 2.5, and the K1 prime, K2 prime can be calculated easily here, right? So R 2.5, R 2.5, okay? This RB is the radius of the pile base, okay? So in this question, RB is equal to R0, okay? Because the cylinder, okay, of this pile has the same diameter from pile top to pile end, okay? There is no bear out on at the bottom, so RB is equal to R0, okay? So directly equal to 0.25, okay? So you can see F13 can be calculated, okay? Be careful about the calculation, a lot of parameters, okay? So you can get this result. So as I mentioned to you, for determining the U value, we just use K1, not necessary to use K1 prime, because you can see that if we use the K1 prime here to determine the U value, then we get this result F13. You can see that this F13 is quite similar, okay? Almost the same to the F13 calculated from K1. I mean the U calculated from the K1, okay? These two values are almost similar, so that's why we said that not necessary to use the K1 prime to calculate the U, okay? Because this K1 using this equation is reasonably acceptable, okay, for determining F13, okay? So that we just use this value here to represent F13. So as I discussed with you about the distance between different pairs of the pile group, right? We actually have 6 distance here, 6 different values of distance, especially for pile 1. Okay, the case will be the same for pile 2 and pile 7 and pile 8, because this pile group actually is symmetrical. Okay, it's symmetrical. We can divide it into 4 groups. For section of 4 groups, okay? In each section or group, we have 2 piles. So that you can imagine that the pile condition for pile 1 is the same for condition pile 2, is the same to pile 7 and 8, right? So for 6 condition, it will be the same to pile 4 and pile 3 and pile 5, okay? So we can divide into 4 parts, but the pile actually can be just divided into 2 types of pile, okay? 2 types of pile. So that, as I mentioned to you, for pile 1, we have 6 different distance. And for pile 6, we have 4 different distance, right? So the maximum distance is 6. So here I list the 6 value for the different distance here. Based on each distance, we can determine one Fij value, right? One Fij value as shown here. So with this Fij value, we can calculate the, or we can just write the expression for the settlement of each pile. Okay, let's see detail later. And as I said, this is a symmetrical problem, right? So consider the symmetrical property and vertical force equilibrium. Okay, let's see the first one, the symmetrical property. As I said, it can be divided into 4 parts, right? So the total load in each part will be equal, okay, will be equal. So that P1 plus P3 is equal to P2 plus P4, okay? These two, okay, they are the same. They are the same. And they are the same, and the total force is equal to 12,000. So for each section, the total force is equal to 3,000 kilonewton, right? 3,000 kilonewton. Okay, so besides, okay, I just mentioned to you, actually 8 piles can be divided into 2 groups, right? 2 groups. The first group is 1, 2, 7, 8. The second group is 3, 4, 5, 6. So that we give a name, okay? 1, 2, 7, 8, we give a name X because they are the same, totally same. The fours are totally same, right? And this group, we give a name Y, okay? So that 1, 2, 7, 8 is equal to PX, right? They're the same. 3, 4, 5, 6 is PY, right? Is PY. So we simplify it, right? Based on the symmetrical property and vertical force equilibrium, we get this simplified condition, okay? Simplified because these 4 are the same, these 4 are the same, okay? And for the influence factor, we already discussed in quite detail, okay? We just show you some as an example, okay? 4, 3, 4, 5, 3, 5, 3, 4, 3, 5, the distance are the same, right? And 1, 3, 1, 2, 1, 2, 1, 3, the distance are the same, okay? R here for this 4 influence factor is equal to 2.5 meter. So these 4 parameters are the same, okay? These 4 parameters are the same, okay? Just show you as an example. Okay, so we can just put the Fij, Fii, okay, of course this is Fii, to calculate the settlement of the pile 3, okay? For example, if you calculate the influence from the pile 6 to pile 3, we use, okay, Py is the force on top of pile 6, right? You can see here, the force is Py, right? Py multiply F36. Okay, the influence from 6 to 3. Okay, and just write down, okay, one by one to be careful about is Py or P6, Px, okay, Py or Px. Then, for example, if we talk about the influence from pile 2 to pile 3, the force P2, the force is X, right? So we use Px here and F32 here. Then we take out the same item, okay, Py and Px out, and we know all the value for this influence factor. Okay, we just further simplify it. Then we get this equation here. This is omega 3 here. Similarly, we can get the omega 1 expression as shown here, right? Okay, there we have 2 equations now, right? And because based on the rigid cap assumption, as we said, the rigid cap assumption, which means this is rigid. If we only have the vertical loading on top, the rigid cap will move only vertically downward, okay? So the amplitude of the settlement of each pile will be the same. Fi will be the same for all the piles, right? As you still remember, in this slide, we discussed about the same thing. Based on the rigid cap assumption, we have the omega 1 equal to omega 2, omega 2 equal to omega 3, okay, omega n, okay, until omega n, they are all equal, okay, they are all equal because the rigid cap assumption, or we can say it is an equal strain assumption, okay? The same, the strain value are the same. So we can conclude that the omega 1 is equal to omega 3. You see here, right? So we can, okay, omega 1 is omega equal to omega 3. So these 2 equations are the same. They are equal. We can get this one. Okay, they are equal, and we can establish the relationship between the Px and Py. Okay, so Px is equal to 1.323 times Py. Okay, another thing, Px plus Py is equal to 3,000 kilonewton. Okay, right? If you still remember here, 3000 kilonewton. P1 is Px, P3 is Py, right? Yx, right? So 3000 kilonewton here. We have two equations for two unknowns. We can easily get the result for Px and Py, right? So with the Px value, Py value, Py, Px value, we can calculate omega 1 and omega 3, okay? But these two are the same, okay? We can use each equation to calculate the result. So omega is equal to 37.9 millimeter. Okay, this large, okay? This slide is for your supplementary information, okay? So if no interaction is considered, which means no interaction between the piles, we only have one pile, okay, or a single pile under a value of the average loading for these 8 piles, which is equal to the total load divided by 8, which is equal to 1,500 kilonewton on top. This P0 is 1,500 kilonewton on top, and we have only one single pile here. And we calculate the settlement. Omega 0 is equal to P0 FII, right? FII, P0 is this value, and FII, we already get it, okay? FII will not change, no matter it is a power group condition or it is a single power condition, okay? No change. Because for calculating FII, we just use K1 and K2, right? It's nothing to do with this R value, okay? So FII, we get it already here. To put it here, and P0, you can see. So the P0 FII, the result is only 7.2 millimeter, okay? It is much more smaller than the pile group settlement, okay? The pile group settlement, we just calculated here, 37.9 millimeter is much larger than the single pile condition, right? Okay, because this settlement for single pile, it doesn't account the influence from other piles, right? We have, if for the 8 piles condition, actually we have 7 other items here, right? 7 other items to contribute the settlement. So that you can conclude that if we consider the pile group, the settlement will be much larger for the single pile, even though the average loading is the same, okay? We call it the pile group interaction effect, which is an adverse effect for the pile settlement, okay? For the pile settlement. So this is just for your supplementary information about the pile group interaction effect, okay? And secondly, if we have another moment on top of this pile group along the long direction, the moment is equal to 6,000 kilonewton meter, this one, 6,000 kilonewton meter. Okay, here you can see we have this moment here. We are going to calculate the settlement of each pile, okay, of each pile. First of all, if we have a settlement 6,000 kilonewton meter here, we can imagine that if we just draw a central line, okay, a central line for the rigid cap, we have a moment on top. So you just imagine this rigid cap will rotate, right? Will rotate like this. And if this is a pile 1, okay, pile 3, pile 5, and pile 7, we can imagine that the force of pile 1 to the rigid cap will point upward, right? Because this pile rigid cap is going to rotate like this, so we will have an upward force from pile 1. Then for the pile 3, we will have another upward force. However, for pile 5 and pile 7, we will have a downward force, right? Downward force to drag down the rigid cap to prevent it from rotating, right? And for the pile 7, we will have another downward force, the direction as the opposite, okay? The direction opposite, okay? And we call it this problem is an anti-symmetric problem. Okay, this is the first thing. The direction are opposite for power 3 and power 5, also for power 1 and power 7. Okay, they are opposite. Another thing is the so-called symmetric is about the value or the amplitude of the loading. Okay, so if we look at in this figure, you can see the direction is opposite, and the value, for example, the this force is equal to this force. Okay, the absolute value of P1 will be equal to the absolute value of P7. Okay, we talk about the absolute value, but the sign actually is reverse. Okay, so it's so that you can see, we just write down the Px, Py here, but the different condition, the different issue is we have negative value here, which means the direction of this force are reversed. Okay, are reversed. So as I mentioned here, okay, even though the value are the same, the value are the same actually, but the direction is reversed. So that based on this kind of understanding, first of all, let's see the moment equilibrium first. Okay, the moment equilibrium, the driven force, which means the external rotation moment, okay, driven moment, and the internal resistant moment, okay. The driven moment obviously is equal to 6,000, right? And the internal resistant moment, okay, let's see this pair first. Pile 1 and pile 7. Okay, let's see this pair. The value for the force, okay, is equal to Px, is equal to Px. And the moment is equal to the force multiplied the distance between these two, right? Between these two. The distance between these two is equal to 2.5 multiplied 3, right? 2.5, 2.5, 2.5. So Px multiply 2.5 multiply 3, right? So this is this pair, okay, pile 1 and pile 7. Okay, how about pile 2 and pile 8? Okay, they are the same, just symmetrical, right? So we will have another 2 multiply, okay, here. So that we will have this one, the second item here, you see? And similarly, for this pair, pile 3 and pile 5, okay, we will have the Py, right? Because the force is Py. The Py multiplies the distance 2.5, right? Then multiply another 2, okay? Because we have another pair here, 4 and 6. So this is the first item here as shown, right? So we further simplify it, we get this equation. Okay, actually from this equation, we have already have one relationship between Py and Px, right? And another issue is we can write down the expression for omega-3 and omega-1, right? Omega-1 and omega-3. And for all the influence factor, we already calculate based on the different radius, different distance, okay? Different distance between two piles, right? So here, the only thing you should be careful is the sign, okay? Is the sign of the from the other piles, okay? For example, this is pile 6, pile 6, pile 6 is here. We have a negative sign for Py, so that this Py is negative sign here, right? For example, pile 2 is here, is positive Px, okay? Positive Px. So we have positive Px here, okay? So we can write this two equation for omega-3 and omega-1, okay, based on the direction and on the different values of the influence factor, right? So we got the expression for omega-3 and omega-1, okay? So let's see another issue about the proportional relationship between 1 and 3, okay? If we say this is power 1 and this is power 3, right? And the settlement between the omega 1 and omega 3, you can see if this one is in the center, and the rigid cap will rotate in a certain angle, alpha, okay? A certain angle. And you can imagine that the settlement of pile 1 is this much, right? And the settlement of pile 3 is only this much, very small, right? Okay. And based on the rigid cap assumption, we will know that the omega 1, omega 3, okay, here, will be proportional to the distance of pile 1 to the rotation center D1 and the distance between the pile 3 to the rotation center D3. Okay, so that you can see we get this equation here because this is the rigid cap. Okay, after rotation, we have this proportional relationship. Okay, omega 1 divided by D1 is equal to omega 3 divided by D3. Okay, here. Then we establish another relationship between Px and Py. Okay, between Px and Py, so that we have two equations for two unknowns. Again, we get the result for Px and Py, right? Should be no problem, right? Because the proportional relationship between the settlement. So we get these two results. Okay, Px, Py value we already know. So we just put back the value into the expression of omega 1 and omega 3. We can calculate it, right? We can calculate it here. Okay, these two actually is wrong. Okay, the first one is omega 3 and this one is omega 1. Okay, because omega 1 is more far away from the rotation center, 1 is more far away from the rotation center, we can imagine that the settlement will be larger than the settlement of pile 3, right? So here you can see the omega 1 is 3 times larger than omega 3, right? So we get this result. We only calculate for omega 1 and omega 3 because they are symmetrical, okay? They are symmetrical. Omega 1 is equal to omega 2. Omega 3 is equal to omega 4, okay? And for the 5, 6, 7, 8, actually, the value are the same, okay? The only difference is the direction. For this 2 pile or for this 4 pile is settlement, okay? Is settlement, downward, okay, downward. And for this 4, okay, it is actually is going up, okay? The pile actually is going up. So we only calculate these two values here as an example. Okay, so this is all I want to discuss with you about the example 3b. Do you have any question about example 3b? Okay, do you have any question? All right. If you don't have questions so far, it's okay. Okay, in SAN. The keyword free hat, okay? Short pile and SAN. Okay, so SAN actually represents that you should calculate the passive earth pressure coefficient. This one, okay, Kp equal to Kp equal to 1 plus sine phi over 1 minus sine phi. Okay, this one you better remember it, okay, just remember it. You should have already learned it in the geotechnical design or in the soil mechanics, okay? This is for calculating Kp, and I also want to, okay, I already told you that you'd better remember this one, right? The mu, this one. So relationship between the shear modulus and Young's modulus, right? And also, I just want to help you to recall your memory for the lecture 1, okay? This equation, okay, is also quite important. So for these 3, I suggest you to remember by yourself, okay? Remember by yourself. So for this condition here, the Kp can be easily calculated here, right? And the Hu is the horizontal ultimate, okay, ultimate horizontal force or maximum horizontal loading, okay, horizontal loading. Here, actually, we just take a moment, okay, at this point, because this point actually we have a force here, okay. There should be another arrow, okay, to point to this red circle, red dot, okay. And if we take moment at this position, we don't consider this p-value, right? Then we can get the Hu from the soil antiforce, okay. So we can get the Hu value, and for calculating the maximum moment, first of all, we cut the pile at this position where the maximum moment occur. Okay, we cut it first. Then we calculate the F value. Okay, F value is the depth of this position. Okay, and then this with F value known and Hu we also know. Okay, so the M max we can calculate from top to this position. Okay, so M max is here. For example, this direction, rotate in the anti-clockwise direction. Okay, we can assume it. Okay, we can assume it, and the Hu we can write it like this. For example, if we assume the anti-clockwise is positive, okay, so the M max here is positive, right? We assume it like this. And then for this HU, you can see if we take a moment at this position, this HU, the direction of moment is opposite to this M max, right? So we will have minus Hu and multiply E plus F. This is the distance, okay? Or the level arm, okay? So level arm between the force and this point, we are going to take moment, right? So because we take the anti-clockwise as a positive, so here we have a negative, right? And for the soil force, you see, for soil force, it's also anti-clockwise. So it is also positive. So soil force is plus, right? Plus the area here. Area is equal to this one. Okay, then F. Then multiply the level arm. Okay, the level arm. The distance is here is 1/3 F, right? Then multiply 1/3 F. You see, if we this will be equal to 0, okay, because the equilibrium of the moment. Okay, so the M max can be written actually here, right? Because we move these two items to the right hand side, negative become positive, positive become negative, right? So we can get the result for M max. This is the final result. Okay. All right. So as you can see from this example, first of all, for this one, we use the equilibrium of moment, right? And for this one, we are going to calculate the F. We use the equilibrium of H, the horizontal force, to get the F value, right? And for the last the last step, the final step to calculate the maximum moment, actually we do the cutting, okay? We do the cutting to separate the pile into two parts, right? And the cutting position is always at the maximum moment position. Okay, we cut it and we can take moment at this cutting point. So we get this result. Okay, so this is three things we normally do. Okay, equilibrium of moment, equilibrium of horizontal force, and the not equilibrium, the cutting. Okay, so cut it to two parts, and then we take a moment. Okay, we take a moment, or we just set the equilibrium equilibrium of horizontal force. Okay, so we may say like this. Okay, sometimes we just cut it first. Okay, we cut it first, and then we establish these two. Okay, with these two equations. So for this one, we get the free head, the long pile, the sand. Okay, this is more simple. Okay, because mu actually has already been given here. The mu, we use mu to calculate hu, right? Only one hinge occur here. Okay, and for this example, you can go through by yourself actually. Free head, the short pile, and clay. Okay, and the maximum. Okay, we cut it first, and we take moment at this position. Okay, for the lower section of the pile, or from the top section of the pile, from top to bottom. Okay, take moment at this position. Okay, we can get these two. We can get these two. Then step by step, actually, we can calculate the F, the M max. Okay, then with the horizontal force equilibrium, if we cut it here, okay, if we cut it here, okay, if we cut it here, the HU, the horizontal force equilibrium, HU will be equal to the anti-force from the soil, right? It means this area of this soil reaction, which is equal to 9 Cu B multiply F, right? This is the area, 9 Cu B multiply F. Okay, we get this result for the horizontal force. So we have another one, the free-headed long pile in clay. Okay, you just refer back the lecture we discussed. Okay, previous notes. Okay, so all the equations are there for different conditions: free head or fixed head, long pile or short pile, clay or sand. Okay, so so I don't go to detail here. So here are just okay, we finished all the examples so far, and we have one example left. Okay, example 5. We will discuss this one in next tutorial. And okay, and for the assignment for lecture 2, we will also discuss in next tutorial next week. So okay, time is up. So if you still have any question, actually you can just send me email